and we're going to move on to the next presentation by Alex Parker from Southwest Research Institute, who will be presenting on self-assembling mesh networks of femto-scale sensor motes for planetary exploration.
All right, so thank you for inviting me to give this talk. I'm going to talk about some novel sensor and communication architectures we've been exploring as part of the Project Espresso program, and that has been under development here at the Southwest Research Institute's new YetiWorks Rapid Prototyping Collaboratory. Specifically, there we go. What I want to talk about is the potential role of self-assembling mesh networks for building out sensor networks on the surface of the moon and the surface of asteroids, and enabling beyond line of sight communication in complex terrains with low power, persistent transmitter nodes. I'd also like to talk about what I think of as an ideal fusion between this type of a mesh network and a particular sensor, which is MEMS seismic sensors, and the ability to build out dense and expansive, low cost, reliable and operationally trivial to implement active seismic networks in at lunar landing sites, either deployed robotically or by humans. So just as an introduction, mesh networks are a form of communication between low power nodes that are essentially peer-to-peer. Every node has the capability of pulling information from another node or communicating directly from one node to another, but the nodes do not necessarily need to talk directly through an RF link direct from node A to node B. If nodes are separated by great distances and there are other nodes in the mesh network in between them, information is automatically relayed between those nodes to reach the target endpoint. These various mesh network standards have been developed over the years. Two of the most common ones that you see utilized in the Internet of Things type architecture are Zigbee and Digimesh, both of which have their own benefits and drawbacks. Both of these enable multi-channel 2.4 gigahertz communication that can support thousands of devices per network that are uniquely addressed, and thousands of concurrent parallel networks occurring in the same space. These networks are self-forming. If a node identifies itself as a member of a network, that network will discover it, and it can seamlessly join and communicate with the network. The network topology will adjust itself to accommodate the new cell and to build new optimal paths for data to flow from any end node to any other node. They're also self-healing because of this nature. So if any given node fails, and it was part of the process of relaying data back to, say, some end node, a transmitter back to Earth, something like that, the network topology will automatically accommodate and find a new path to get data back to that end node. So I'm showing here a real recording I made of a network we deployed in Boulder, where we're forcing failure. I'm pulling batteries out of individual nodes. This is sped up vastly because it took me a while to walk from node to node, as these were spaced out across several hundred meters. And then we reintroduced some of the nodes. So the nodes are all communicating data, seismic data, back to a base, which was my laptop, and was connected to the network. And I killed 3 of the nodes that were closest to the laptop and enabling a lot of the data relay. So this impacted the strength of the data link because it was now having to communicate further, but the network healed around those failures and then reaccommodated as soon as those nodes were brought back on board. So this is a basic overview of the advantages of a mesh network type topology. As I see their role for lunar exploration, there's this really ideal pairing, which would allow us to do sort of a 21st century version of the Apollo ACE and lunar seismic profiling experiments. Instead of deploying 3 or 4 geophones in a limited array around a landing site with wired connections, using something like a mesh network and low-cost MEMS devices could enable the deployment of many tens or even hundreds of low-cost, extremely durable seismic sensors over vast areas with varying degrees of local density. This would allow you to probe many of the questions that were discussed in earlier talks about seismic hazards in terms of local seismic properties, and develop a great deal of understanding of the properties of your site locally beneath your lander. Because of the sensitivities of modern MEMS devices, we can use existing operations to provide the acoustic signals necessary to do this. This includes things like hammering, drilling, or the stage impacts or takeoff from something like a crewed lunar lander. Additionally, this can create a communication backbone where other sensors can be communicating back to any given node, and they don't have to be seismic sensors. So for example, if you want to have the sensors that were providing informatics for Kelsey's talk earlier, if we want to get information from one astronaut's radiation suit sensor to another astronaut's radiation suit sensor, they don't have to communicate direct line of sight. They can hop over this network trivially, and the network itself is agnostic to the content of the messages. This all started when we were investigating a potential mission concept of using magnetically anchored seismic motes for asteroid seismology. This is an illustration of one of our fully functional anchored motes. These caltrop landers can actually cling to simulated regolith upside down in 1G. The degree of magnetism in this regolith is sufficient that we can vastly exceed the surface gravity holding force on a low G asteroid. But the challenge was, how do we get the data back from tens or hundreds of these on the surface of an asteroid? And the solution we came to was building a mesh network on the surface where any sub-parent spacecraft node was able to relay material data from over the local horizon through the mesh network of the adjacent sensor nodes. Building from there, we have been thinking about how we could deploy a ground spike type, something more like a traditional geophone type network that an astronaut could deploy or a rover could deploy. So we built this demonstration network of 9 nodes, 6 of which are seismic nodes using a placeholder accelerometer, not our flight-like accelerometer, 2 of which model mobile instruments, something like a handheld fluorimeter, and another like a radiation sensor. It uses a UVC sensor to measure a UV index. All of those communicate back to a base node and can relay any set of information to any other node. These have extremely low power operation. They all have onboard batteries, and with those onboard batteries, they can run for 48 hours continuously at full TX. So these are not how you would deploy them on the moon, but they're a very promising first step toward doing so and enable us to do live field testing. This is a quick illustration of a crude block diagram of the concept seismic nodes we're talking about, as well as an illustration of the sensor we have in mind. This is a commercial MEMS seismometer used in oil and gas exploration. They're extraordinarily sensitive and relatively low cost. These units are under $3,000 a piece, and they've been proven. They're used all over the world for, like I said, oil and gas exploration and seismic assays. They're very low mass, very low power, and have a very well-matched bandwidth and noise density for doing the kinds of active seismology that we'd want to do on and around lunar landing sites. As I mentioned before, we could also use it for heterogeneous mesh networks, where this backbone of seismic nodes builds a mesh network that enables portable devices to communicate back to a lander, or lander to communicate to a HUD or other informatics device seamlessly and with very low power draw for any given device in the network, thereby increasing the potential rain and terrain access. You don't have to worry about maintaining direct line of sight access between your astronaut, any other astronaut, or any other.
You're at 8 minutes.
Thank you. This is an example of real-time data streaming back. I've actually sped this up for the purpose of the top, showing a heterogeneous data return, recording from the seismic network, 1 second pings from the radiation sensor, and geotagged fluorimetry measurements from our handheld fluorimeter, all being shipped back over the common mesh network to a source node. So any node has access to this data and could be displaying it on a heads-up display or some other display if necessary. Finally, we've been doing testing using vehicle-induced signals, something like that you get from a rover operation, as well as signals from rotary hammers, rotary hammer drills like those showed yesterday by the Honeybee team, and have been using these as test cases to see how we would deploy our ground stations to recover seismic information at landing sites. But bear in mind, looking at these relatively noisy measurements, one, these are being done under Earth atmosphere and windy Colorado conditions with no shielding. And two, these particular IMUs are 1,000 times less sensitive than the baseline flight IMUs that we are planning to use. So I'm going to put up this slide as my conclusions. Our next step, we're going to be working on integrating the flight-like sensor and doing some environmental testing, thermal vac and radiation. We're also working on a long-range DART deployment system, something that can be fired from either a crossbow or a mortar-like system that would enable deploying this from a stationary land over very large distances, and then conducting analog field campaigns. And in conclusion, these tiny sensors, again, these mass less than 100 grams a piece, all up, including power systems, comms, the sensor superstructure mechanisms, everything, could enable some really transformative lunar science at landing sites and provide this extremely valuable communication backbone. And do we still have any time for questions?
We should have a couple minutes for questions.
Great. Then while we're fielding those, I thought I would tempt fate and actually do a live demo. I've set up the entire network in our Boulder laboratory, which is a notoriously seismically active building. And I'm going to ask my laptop to join the network and start querying one of the seismic nodes. And I'm going to plot a live spectral density of the building vibrations, which should come up here in a second. There we go. So this is live flowing through that mesh network of seismic nodes as deployed through our building. I do not have a direct line of sight between my laptop and the sensor node that's relaying this data. The data is flowing through the network of active nodes. So if there's any questions, I'd be happy to field them.
There's a question from Nick Schmer. What kind of sampling rate can the network accommodate, and ultimately what kind of bandwidth, megabytes or kilobytes?
Right now, with a single network layer, I've been able to accommodate a real-time, basically 10 stations deploying 3-axis 16-bit 100 hertz seismic data. We found that if there's a second layer of the network that works more as a serial network, and we have onboard ring buffers, we can increase that massively, several hundred times. So I think we wouldn't necessarily need to be streaming this data in real time back to the base stations. We can put gigabytes of storage on board these individual nodes and query them at any given time to pull data from any given site. So for example, if we know there was a drilling event and we want to take the 10 minutes around that drilling event and ship that back, we can ship back 1,000 hertz, 24-bit, high quality, uncompressed seismic data from every node in a 1,000 node network in a very reasonable amount of time. So that's kind of the trade-off there. If you want to do real-time streaming, what I said before, about 10 nodes reporting about 100 times a second, 3 axes is about what I've been able to accomplish with the commercial single layer network.
Madoon Menon has a question. He asks, for the mesh networks, are timestamps also relayed with data packets?
I'm relaying them. One of the challenges is, of course, providing a coherent and well-synchronized time signal across all of these. On the Earth, that's easy to achieve with GPS. On the Moon, we don't have that right now, although some of the talks we saw yesterday is, that's a high priority item to provide some kind of a timing asset. So I have included a time synchronization scheme in the way the nodes communicate, which right now I would be willing to, using my synchronization standard, I'd be willing to argue that the synchronization is good to a millisecond, and that is extremely preliminary. We can definitely do vastly better than that, but that's where we're at right this second.
All right, that concludes our time for questions. Thank you for that presentation, Alex.